Hello, in this video we use characteristic function and moment generating function to define new moments indirectly from your distribution, which we will call them cumulants. Cumulants have interesting properties, particularly when you're dealing with multiple random variables. So what are the cumulants? Cumulants are some moments which are defined using the second characteristic function, second moment generating function, and so on. Basically using the logarithm of your function. So if you we define the cumulants of order n as you calculate derivative of your second moment generating function n times, and you replace s by 0. Okay, so this is using second moment generating function. Basically, you remember that psi x of s is ln of your moment generating function s of x of s, and basically is logarithm of integral from minus infinity to plus infinity of e to the power sx f x of x and dx. Okay, so it's like, it's not a direct moment, it's indirect, but it's related to other moments, and we'll see what interesting. Because basically you're looking at the moment generating function or characteristic function is in a log domain. So if the moment generating function is a product of some terms, in the log domain they become additive. So multiplication becomes addition, and this makes things simpler. So in those applications that you need to convert a product into summation or additive things, problem becomes easy to solve. So this is why cumulants, they have some application. This is why they're important. So now the second moment function, which is log of the characteristic function, you can write a Taylor series expansion, and by virtue of this definition, the Taylor series coefficients are cumulants. So cumulants, these guys, are Taylor series coefficients of the second moment function or second characteristic function. But these cumulants are related to moments because you say that this guy x of s is equal to ln of the x of s. So if you take log of this one, so we say d to the s of psi x of s is equal to derivative of this one, the phi x of s over ds divided by phi x of s. Okay, so you see this is where the relation. So using this expression, you have this one, or if you take the second order derivative, you can get this one and so on. Now, if you replace s by 0 here in this expression, this guy becomes 1 and this guy becomes equal to this one. So, and then now if you replace s by 0, this is 1, and then you get this guy becomes equal to that point s equals 0. So you see that the Taylor series coefficients of first moment generating function and second moment generating function, they are related in a linear fashion. So from here, you could easily calculate the first cumulants is equal mu x, and the second cumulant is variance, okay, because and so forth. So the cumulants in next chapter, when we will deal with multiple random variables, if you have multiple random variables, if you add them together, the cumulants of the sum, all the cumulants of the sum is equal to sum of the cumulants. This is valid for all cumulants. So this property is what makes it applicable in some algorithms. So let us have a final example for this chapter, which is determination of density function of a random, the function of a random variable, which we have dedicated a chapter to it. But this is just one example. You can use the moment generating or characteristic function to solve this problem But this solution is not universal. You cannot apply these to all application. An example, sometimes it helps, sometimes not. So here what we know is that characteristic function of y given by this one. Now in this example you can replace y by g of x, and then this becomes integral of e to the power of j omega g of x, and then f x of x dx minus infinity to plus infinity. So both integrals will be equal to each other. In this one you need the distribution of x, in this one you need the distribution of y. But if you have the distribution of x, you can directly calculate this one and then apply the inverse Fourier transform. So you can do that, or directly you can use this equality, and if you have these somehow manipulate that, you can extract f by y directly from the integral. So these two integrals are equal, and then we can use it. So you can use this relationship to determine PDF of g of x. So as example, suppose that x is normal with mean of 0 and variance of 1, and x is equal to let's say x to the power 2n. So if you put this one in this second equation, so you can get this expression. The first integral in the previous slide gives you another. So here this x is a dummy variable. So you could say that x to the power of 2n, you could say y. Okay. Now if x varies from minus infinity to plus infinity, if x here is 0, if x is minus infinity, y starts from this is, let's say, y, because you have a function like that. So y starts from positive infinity to 0 and then goes up. So here y varies from positive infinity to 0, and then from 0 it goes to plus infinity. So basically what I have to write this integral, if I change this dummy variable in this integral, I have to write twice, because y spans the area between 0 to plus infinity twice. Once here, twice integral y varies from 0 to plus infinity, and then e to the power j omega 2 x becomes e to the power of j omega y, and then x2, from this expression you can get y is equal to 1 over n is equal to x to the power 2. So here you replace this x2 by the root of order n of y divided by n, and then from this expression you have x to the power of 2n equals y. So if you can take derivatives, so dy becomes equal to 2n x to the power of 2n minus 1, and then dx. Okay. Now you have to replace this x by y, so you get dx from this equation is equal to dy divided by these 2n, and then divided by x to the power of 2n minus 1. So from this equation, so y to the power of 1 over 2n is equal to x. So you replace this one by this one. So you get dy divided by 2n, and then you get y to the power of 1 over 2n, and then to the power of 2n minus 1. So this expression, you replace it by this dx. Okay, so this dx goes here, and then I get this this equality. So from this equality, okay, and I know that this should be equal to also integral of e to the power j omega y, and then f y of y dy from 0 to plus infinity, because from this expression I know that y is a non-negative random variable, because you have x to the power 2n. So this is why I started from 0. So comparing these two integral, or comparing this equality, Okay, the range here varies from 0 to plus infinity. This and here you have the same thing. E to the power j omega y, a to the power j omega is equal. You have dy, you have dy. So the remaining part here, so I make it, so this portion should be equal to Fi(y). So Fi(y), first of all, is non-zero for positive values of y. So this is why I have uy here. And this part is this one. Okay, so indirectly, I was able to use the moment generative function in order to calculate Fi of y directly without those steps.